Hello and welcome back. This one is a doozy. 2023 day 5. Um, let's get into it. So this is probably, I think the theme for this year has just been kind of harder than usual, more early on. So if you got stuck on this one, I can't really, I can't really blame you. Don't feel bad about it, okay? Um, so for day 5, um, you get this sort of input where this is similar to a lot of different events of code where you have a bunch of groups that are separated by um, empty lines. And the idea is that your first group denotes some seeds. And then the following information, um, each one of these sections of numbers basically details some transformation rules. Um, and you're going to be applying your transformation rules on your list of seeds as you go from top to bottom through all of these categories, right? And then once you've finished applying all of the transformations, you look at your seed value at the end, and in this case, it asks you to get the minimum. Okay, so how are these transformation rules actually encoded? Well, so you might have noticed that they are all in groups of 3, and they're ordered in kind of a weird way, so you have to pay attention. But where is, oh, here we go. The destination range start, the source range start, and the range length. Okay, so each one of these rows defines some sort of range that ranges that your seed values can fall into, right? And it starts with the destination range start, but let's look at the source range start first. So the idea is that you start at the source range start, and then you construct a range from there up to basically however long the range length is. So like in this first row, your source range start would be 98, and you increment by 2. So the numbers that would be included in this range are 98 and 99, right? So the source range start is inclusive. And then, excuse me, it says, and then the first parameter is the destination range start. And you basically use this to transform numbers that fall within this range into whatever the destination range start is. So you can think of this as defining a mapping from the numbers 98 and 99. So that's the source range start plus plus the range length. So we're looking at 2 numbers in the range. And if one of your seed values falls into that range, then they get transformed into the range starting at 50. So 50 and 51. In this very first row, that means that the number 98 would be transformed into 50, and the number 99 would be transformed into 51, right? This paragraph under here sort of outlines what I'm saying here. And then the same for the second row. We have a range from 50 to 98, I believe. And essentially what's going to happen with numbers that fall into this range is based on the destination start, they're just going to get incremented by 2, right? So you're just moving the start of the range up by 2. Okay, and so what you do for each one of these categories is you kind of put together, you parse this out and you put together all of the ranges for each category. One way you can think of it, and in fact how we're going to be implementing it, is you can think of this as a reduction across all of these transformations from top to bottom with our seeds, the seed values as the initial value. And so we'll start with our seed values. We will apply the transformation rule in the first step, and we'll get some transformed seed values. We take those transformed seed values and we apply them into the transformation on the second step, et cetera, et cetera. And then at the very end, once we've applied all of the transformations, it says find the lowest location number. This is basically asking you to take the minimum of the resulting set. Okay. Now, normally I would, Alt-Tab, and we'd just begin solving part one. But actually, we can write a function that solves both part one and part two. So hopefully this part all sort of makes sense because it's about to get a little more difficult. Okay, so part two says, hold on, actually these seeds are not discrete numbers, okay? The seed row itself specifies a series of ranges. And the way that it does it is you look at each pair with no overlap. So 7914 would be a pair and 5513 would be a pair. And you construct a range by basically like 79 plus 14 is 93. So the numbers from 79 to 93 would be one range. And then 55 plus 13, 68. So the numbers from 55 to 68 would be another range, right? Or actually it would be, I ran into this a lot because there's a lot of opportunities for off by one errors here. But this basically says like, okay, it would actually be 79 to 92 and then 55 to 67. Let's just watch out for this. And then once you put together all of the ranges for the seeds, now you apply the same transformation rules, but you're applying it to all of the seeds that, the seed numbers that are contained within those ranges, right? And spoiler alert, the ranges are extraordinarily large. There's, I don't know, at least millions, probably billions of seed numbers contained in these ranges. So you can't easily, I know people have done it, but you can't easily just brute force through all of the seed numbers to be able to figure out which one is the minimum once you get to the end. But anyway, part two again asks you to, basically the only difference is that you are taking the ranges instead of the discrete seed numbers. You apply the same transformations, and then once you've applied them all, what's the minimum of the resulting set is essentially what this is asking. Okay? So the reason why I dove into part two right away is because we can write a single function that just deals with the ranges. And when we want to convert the seed values, we can just encode these as a one element range, right? So like instead of 7914, it would be a range from 79 to 79, just including one number, 14 to 14, et cetera, et cetera. And that way we can run the same function for both parts one and two. It'll be a little bit trickier, but it will make the code somewhat nicer. All right, well, anyway, enough monologuing. Let's get into the problem. So we are going to be doing this in NGNK today, and that is, I mean, NGNK is nice to work with in general, but specifically for today, it has one killer feature, which is a particular way that it handles its reductions, which I will talk about a little more once we get there. But yeah, first we're going to be looking at the test input. So let's just load the test.txt. That's just this from the problem description, right? And then we want to be able to split on empty lines. So we can use the cut function here. And we're going to be cutting on, for each p, length 0 equals. So these empty strings have a length of 0, and we're just selecting for those. We'll do where to get the indices of those in that Boolean vector, and then we'll prepend 0 so that we don't lose the seeds row at the top. And we'll assign this back to p, and then we might as well parse out our seed row while we're here. So we get the first row, the first element. We can split this on spaces. We don't care about the seed word, so we can just drop that. And then for each one of these, we can eval them to turn them into numbers. And we'll call this S for seeds. And now we have our seed row. Okay, and then we want to, basically the parsing rules for each one of these is going to be the same. We don't really care about the category names. We just care about converting these into ranges. Okay, let's take a quick detour, all right? Because we're going to be heavily using something called, in ngNK, it's called bins or bin search. In Dialog APL, it's called interval index. I've used it quite a bit in my other videos. But the idea is basically, so given a sorted right argument, let's do like 4, 8, 12 here. This apostrophe here, when you give it to numeric arrays on either side, is bin search. So given a sorted left argument, it will tell you the how do I put this? It will tell you the index of the greatest. It will tell you the index of the greatest number in the left argument that is less than your right argument. Just sort of a mouthful, but I can. So like if you search for 5, it will tell you 0. And remember, in ngNK, we're 0 indexed. Okay, so it's basically saying, okay, your number 5 is greater than or equal to the first element. And if we do 9, it will tell you 1. Actually, maybe I can just do like 13, like this. And we'll just search for all of these. Okay, so you can sort of see the indices going up as you get into different ranges, right? The thing about bin search is the lowest number that it will give you is -1. And this basically means that it is beyond the left bound of your left argument. And the largest number that it will give you is the index of the last element in the vector. And it will basically say like, okay, your item is greater than or equal to the last item in the vector, all right? We are going to be heavily using this. Basically, our whole solution sort of hinges on the behavior of bin search and creating some arrays to make working with it somewhat nicer, all right? So that's just an aside. Keep that in mind. Okay, back to parsing. So first, let's just focus on getting the numbers. So we have p. We can do one drop p to get rid of our seed row. And then for each one of these, we can drop the first 2 elements. And then we can eval each of the remaining ones. That will turn them into numbers from strings. And then it's going to be super helpful if we sort these. And I think that the easiest thing to sort on would be the source range start, which is the middle element. So let's see. So we can sort. We can select the second column with semicolon 1, and then we can sort like this. And yes. So what we're doing here is we're parsing out all of the numbers. And then for each one of the sort of 3-element pairs, we're sorting by the middle element. And this basically means that we're sorting by the source range start, right? And let's call this R for like rules, I guess. Okay, and then remember how I was talking about interval index or bin search in G&K? It would be cool to have some vectors to be able to operate bin search on. So what we can do is for each inner element of R, we can drop the first element. That's the destination range start. We don't care about it quite at this moment. And then we can do a plus scan. And this basically converts, so remember this second element, which is now the first because we dropped the first one. The second element is the range start, and then we have a range length. And so what plus scan does is it just adds the range length to your range start and gives you sort of an upper bound for the range, right? And then all we have to do is put all of these together. So for each row, we just concatenate everything. And you'll notice that we get these nice sorted vectors. And these constitute the sort of the range boundaries for each one of our sets of transformation rules. And these vectors are sorted. They're going to be nice to use bin search on, using these vectors as the left argument. Now, you have to be careful here. So it may look like, you'll notice we have a lot of duplicated elements. And basically what's going on is not all of these ranges are actually valid. So 0 to 7 is a valid range. 7 to 11, 11 to 53, 53 to 61, etc. These elements between numbers of the same ones are not valid, which, by the way, I should have mentioned this in the problem description. But if let's see, any source numbers that aren't mapped correspond to the same destination number. So basically, numbers that are not part of valid ranges don't have any sort of transformation applied to them. So that is useful to know. Anywho, you might look at this test input and you might say like, okay, well, it seems like all of the ranges are contiguous, or there aren't any gaps between them. And that is not necessarily true for your actual problem input. So just be careful about making that assumption here. Anyway, we'll assign this to M for map, I guess. And now we need to come up with the some numbers for the transformation rules. And basically, for the transformation rules, we're basically translating a range, up and down by some amount. And the amount that we're translating is equal to the difference between the destination start and the source start. So we can, again, look at our rules for each one of these, we will do, we'll take the first two elements, because now we don't care about the range length, and we can find the difference like so. And these are sort of these are the values that get applied whenever one of your numbers falls into a valid range, okay? But, if we look at M, like I said, only some of these ranges are valid. So like 0 to 15, 15 to 52, et cetera, et cetera. We need some way to say like, okay, if you get a -1 when you're doing a bin search, it's not valid. If you get a 1, it's not valid because it falls between two of your valid ranges. If you get a 3, it's not going to be valid. And so basically what we can do, so because numbers that fall outside of a valid range don't have any transformation rule applied to them, that's the same as like adding 0, right? So if we look at if we look at the sort of the transformation, offsets, let's call them, that we're calculating, if we want to line these up with indices that we might get from bin searching in our map, we can just we can surround each of these elements with zeros, and then basically these only apply for matches within a valid range, and then on either side of them are going to be invalid ranges, right? So we can do that by prepending a 0 here. And then for each one, we'll run a function where we put a 0 on the end, like so, and we just concatenate everything. So this is just taking our offsets that we calculated and putting kind of interspersing zeros around all of the values. Okay, so let's call this T for like transformation offsets. Okay. Naming's hard. The interesting thing about what we've constructed, so we have our map, which we'll use to bin search against. This tells us sort of the range boundaries. And then we have our transformation offsets, and this tells us how much we're transforming the range, the seed values, as they fall into different buckets. If you look at the length for each one of the maps, and if you do the same for our transformation offsets, you will notice that the length of the transformation offsets is 1 greater than the length of our range maps, right? And the reason that's the case is because when you do bin search, again, you get the possible values that you can get for bin search is basically 1 greater than the length of the array you're searching in, and that's because you can get -1 if it falls outside of the left-hand side. And so by having our transformation offsets having their length 1 greater than the range maps, this means that we can freely bin search within the range maps, and then we know that we won't get like indexing errors when we index into our transformation offsets, right? Hopefully that makes sense. But anyway, this is all that we need from the input. So our input is fully parsed. We don't need it anymore. And basically, we're just going to be working with, again, the range boundaries and the transformation offsets. Okay. Now, the tricky thing, so first of all, because we're going to be working with ranges exclusively, we sort of skipped the easy part 1 question, and we're just diving into the deep end here. The first thing that would be useful is a way to split ranges depending on the boundaries that they fall, right? So like if in M, so like if we look at the first row of M, we have 50, 98, 98, 100. If we had a range, let's say that we had a seed range from like 20 to 120. Well, we have to break up that range because the numbers within that range are going to have different transformation offsets applied to them, right? And so ideally, we would want to break up the range so it's like, again, if we started with like 20 to 120, we would want, 20 to 49, 50 to 97, 98 to 99, and then 100 to 120, something like this. And so I think the very first thing that we can do is we can write a function to split ranges for us. Let's say that our function, will work with the first row of our range maps here. And for simplicity's sake, we'll just pick a range that sort of spans the entirety of it. So we'll use 20 and 120. The first thing that we do with this function is we perform bin search. So searching within our range boundaries, we look for the range that we're specifying here. And we get -1 and 3. So that 20 is outside of the left-hand boundary, so we get -1, and then 120 gets 3 because it's greater than the index of the last element, right? Now we need a way to sort of fill in the missing range values. So between -1 and 3, there's 0, 1, and 2, right? So we'll do kind of a parameterized iota here. We can look at the difference between these two. We can negate it, and then we can take the range 0, 1, 2, 3, and then we add the element. By the way, let's assign this to I, and we add the first element to make sure that we're offsetting it correctly, right? So now we've constructed this sort of range of numbers to make up for the missing elements. But if you think about it, -1 isn't really going to get us anywhere. So let's add 1 to this, right? If you have a range, so let's say that you did like bin search, and let's say that you did bin search and you did like 15, 25, right? So you get 0 and 1. The element in the left array that's between your two numbers is 20. It doesn't have anything to do with 10. And so if you do 1 plus, then you get you get the index of 20 here, and you're able to splice that in. So yeah, we add 1 here, and then I think it makes sense to just index into our map at this point. So because our range is 20 to 120, essentially what we've done is we've said, okay, all the elements in our map are between the two numbers that we passed in, right? Let's assign this to A, and now we know sort of the range boundaries that are between the two numbers that we passed in, and all that's left to do is sort of construct the ranges, right? And when you're constructing a range, it's going to be from some number to one of these boundaries -1, and then you'll have the boundary, and then you'll have the next number, et cetera, et cetera. So we can just we can do a -1 plus here, and then we can concatenate A, and we can concatenate our initial values, and then we can sort them, right? And then we can basically just put them into pairs by doing a reshape here. Remember that with NGNK, when you pass this null value into reshape, you don't have to specify that dimension. The interpreter will figure it out. And lo and behold, we've transformed our range of 20, 120 into a bunch of new ranges. And these are exactly, if we look at like the first row of M, these are exactly what we would expect. So we've split the range into 20 to 49, 50 to 97, 97, 98, 98, 99, and then the remaining numbers, so 100 to 120. And we can sort of play around with it to make sure that we're accounting for all the different edge cases. So if we do like 10, 20, meaning that both of them fall off the left side of the range, we get just 10 and 20, which we would expect. If it oversteps the left bound, we get 10 to 49, 50 to 60. If they're both off the right side, so like 120 to 140, we just get those numbers. if you did like 99, 103, you will get a range of 99, 99. By the way, this is how we're deciding to encode single numbers, right? And then you get a range from 100 to 103. So this seems to work, and we can basically call this function like f, I don't know, for function. But this basically will take, so we've constructed a function that will take it takes a range boundary map, and then it takes a range, and it will split that range according to the contents of the range map, right? So this is going to be super useful as we're sort of moving down. And speaking of moving down, it's time to talk about that reduction thing that I talked about a little bit ago. So ngNK has very useful behavior when it comes to reduction. First of all, reduction in K, unlike in APL, which I hate, but it is what it is. Unlike in APL, it actually operates left to right. In APL, you have this because of some like legacy stuff going on, all reductions in APL happen right to left. So you end up doing a lot of reversing. And also, ngNK will allow you to specify an initial element, which is nice. But not only that, you can specify an initial element and then a number of other vectors or arrays. And as long as those arrays have the same length, you will reduce down all of them. And you get each one of the elements. Maybe it's easier to just show. So I can do like plus reduce. And let's say that I give like an initial element of 5, and then like iota 10, and iota 10, I don't know, 5, 12 plus, whatever. So the idea is that our initial element is going to be 5, and then we have 2 arrays, and we're going to be reducing down all of them, right? And this is super, super useful because rather than, for example, like constructing a list of indices and then having to like index back into some other arrays all the time, you can construct the reduction like this, and you get all of the information that you need right there. So it's super useful. Okay. So let's do a reduction on, let's say that our initial value, which our initial value is going to be some list of ranges. So we'll just start with 20 to 120. And then let's start with the first row of our mapping input and the first row of our transformation offsets. And we're going to write some function here. Okay. The implicit names in ngNK are from left to right are going to be X, Y, and Z, or Z for you non-Americans. So the first thing that we're going to want to do is we want to run some inner function for each range in our leftmost array. And this is where things start to get a little bit tricky because ngNK does not, like if you define a value in a lambda, that binding doesn't carry down into other functions that you may specify within that lambda. So it doesn't have, geez, I'm blanking on what it's called. Lexical closures, something like this. But basically we have to kind of implicitly pass the arguments around. So we will, for each X, we'll do a function that is already partially applied on our map and our transformation offset. Okay. So now in this inner function here, now we can do, well, we can call f our range cutting function, and we can call that on x, which is now our range boundary map, and we can call it on z, which is a single range from our list of ranges. And if we do that, hey, it works. So this is a little bit tricky with all the remapping that's going on with the x, y, and z. It's a little difficult to keep track of, but you know, stick with me here. So this output from our range cutting function looks like what we would expect. The only thing that's really left to do now is to apply the transformation offsets. And so what we can do is let's assign this to A, and then we are going to add the transformation offsets. The way that we find them is for each one of these ranges, we take the first element, so the start of all the ranges, right? And then we can do a bin search for those starts within our range boundary mapping. And then we add 1, because remember, when you're doing bin search, sometimes you can get -1. And so we're basically just shifting those into valid indices. And then we can index into it using our transformation offsets. And you get this, which is all of the ranges have been split, all of the transformation offsets have been applied, and all that we have to do now is within this kind of outer function here, we just concatenate everything together because we're doing a each, and so we're going to get a vector of ranges, and we want to concatenate that down into just a vector of ranges. So we get this. And then let's see. So for part 2, what was it? Okay, yeah. So for part 2, we look at our seed values and we construct ranges from them. So that's not too bad. Basically, here's our seed values, and we can do 0 and 2 reshape. So we're just splitting them into pairs. And then we can construct ranges out of them by doing a plus scan on each row, right? So we can do that. We can run our function here on those ranges. And then rather than just doing the first row of our maps, of our range boundaries and our transformation offsets, we'll do the whole thing. And these are the resulting ranges after reducing down all of the rule sets. The problem asks us to find the minimum, which is basically going to be the some left side of some range. So we can just concatenate all of these, and then we can find the minimum, which is 46. For part 2, for the test input, that is the correct answer, right? So this function, let's say, okay, we're gonna partially apply this function, and then the rest of it can be a train. This is already in train format, so let's just assign this to G, and now we can just run G on this, and we get our part 2 answer, right? For part 1, we're going to do the same thing, except that we consider the seed values as single value ranges. And so we can do that by just doing a for each 2 take on each one. And then we run G on it to find 35 is the minimum, which is the answer for the test input for part 1. So hopefully that makes sense. When you put it all together, it looks like this. And I think this is like fairly array based. I mean, we work with these large arrays of the range boundaries and the transformation offsets. The only tricky bit is this row here, kind of our function where we put everything together. There might be a nicer way to do this without basically doing all this rebinding of the x, y, and z parameters or arguments. But it's still like relatively short. And let's just make sure that it actually works. So if we run it on the actual problem input, we get 515, 806, 74. Which is the answer for part 1, and 997, 512, 40, which is the answer for part 2. So yeah, that's the solution in K, and interestingly enough, so there's a timing function in K which you can use to gauge performance. So if we wanted to like run part 2, just part 2, this doesn't take into account the parsing and everything that went before it, so it's not fully representative. But if we run it 100 times, it takes 53 milliseconds on this machine. So I guess you can infer that running part 2, a single instance, takes around half a millisecond, something like that. Again, this is just running part 2, doesn't take into account the parsing and building of data structures, but it's still quite fast. So I'll take half a millisecond over some of the crazy times that I saw in the Reddit thread where people are, heating their homes in winter by brute forcing for 16 hours. You know what though? More power to them. There's nothing wrong with that. So yeah, that is day 5. Again, a difficult one. But yeah, ends up being a fairly interesting problem in the end. Yeah, this is my longest video so far this year. So if you made it this far, thanks for sticking around. And I will see you next time.